Hi everyone. In this video, we will define a surface integral of both scalar fields and vector fields, and also examine some fundamental properties of those integrals. So to begin this video, we want to start simply by defining what the surface integral of a scalar function is. So let S be a parametric surface described by some differentiable function R on a region T in the UV plane. So to begin, we have our usual setup, right? We have some region T in the plane, the UV plane, and we're mapping that via this differentiable function R to some surface in R3. Okay. This is my surface S, which is simply R of T. All right. Now, if I have some scalar field, let's imagine I have a scalar field F, which is defined and bounded on the surface S. So maybe it's defined on all of R3, right? But at a minimum, I want at each point on my surface S, this function F, which is a scalar function, to be defined. So at each point on this surface, my function F takes as an input a point on this surface and spits out a scalar value. Okay. So if I have all of those things defined, then I can define the surface integral of F over the surface S, which we'll denote as, this looks like a double integral, but it's really a surface integral. So it's the integral of F over the surface S. We'll define that by a double integral. So this is the double integral over the region T of F of R of UV times the norm of the fundamental vector product dr du cross dr dv du dv. All right, so let's sort of think about what's going on here. So the idea really fundamentally is we want to take all of these, we have a bunch of little function values, right? At every point over here, right, we have some function value. So obviously I can't draw all the points on S, but you just imagine, right? At each of these points, right, my function has some different value. And so what I want to do is I sort of want to think about taking and adding all of those up. But at any particular one of these, right? So let's say I have some point here, UV, right? It's going to map over here to one of these points. Okay, great. But if I think about sort of partitioning this up in little pieces, right? So maybe I sort of partition this up into this little element, but when it comes over here, right, it doesn't come as a perfect little uniform square. So you can imagine if I sort of gridded all of these off, right? When I come over here, that's not going to grid perfectly because that parameterization is stretching and compressing these differently. So this first little piece right here, right, that I've colored in, it's going to come over here as some sort of other, parallelogram looking thing. Okay. So while I want to add up the value of F, I also need to recognize that maybe at this point, this is taking up a lot of space or a little space. So what I'm going to do is I'm not just going to add up all the values of F. I'm not just going to integrate F. I need to multiply F by that local magnification factor, which comes from the fundamental vector product. So we talked about this in the previous video, this notion of the magnitude or the norm of the fundamental vector product giving you some sort of local magnification factor. Okay, so really what I'm doing is I'm taking the values on the surface, but I am weighting them by that local magnification factor. And then I'm adding all of those things up over every u and v in this region T, right? So what I'm really doing is I'm coming over here, I'm integrating over this region T, but I'm aware that this region T is being mapped over here to my surface, where both that's giving me some different function values, right? So the UV gets plugged into R, so it gets mapped to my surface and then plugged into the function. And then I also multiply by this magnification factor, which helps me understand that even though when I'm calculating this double integral, I may be weighting u and v equally, this mapping R does not necessarily weight all u and v values equally, right? It magnifies and possibly compresses them locally right? And that's what comes from this factor here, the norm of dr du cross dr dv. Okay. All right. So this is, though, just a definition. I've given you some maybe motivation for what it's actually doing, but this is just the definition of the surface integral of f over s. And it's defined in this way whenever this double integral on the right exists. And as you can imagine, because we're defining it in terms of a double integral, right, all our normal theorems about double integrals exist. So if you assume that, that this quantity is sufficiently well behaved in terms of u and v, and that f is sufficiently well behaved in terms of u and v, of course, that double integral will be defined. All right. Now, an immediate sort of consequence of this actually is, if you just took this function f and you replaced it by the constant 1, well, what you get is you get the area of the surface, right? If you sort of weight each point on the surface in terms of its value equally, then you just get all those little surface elements sort of added together, which are really just giving you the surface area. So if you just replace that f by 1, then that just gives you the area of the surface, A, which we could call A of s, is just the double integral over t of the norm of this fundamental vector product. Again, you've just replaced that f with the constant function 1. All right. Let's remind ourselves again, this is something you almost certainly did in Calc 3 course, but it could have been a while. So let's maybe work through one example of that first. Now, you may want to go back to the previous video where we talked about surfaces and fundamental vector products. We're going to continue with that sphere example since we've already done a lot of the calculation for that. So if you need to, maybe go back and remind yourself, what was that parameterization of the sphere? How did we come up with that fundamental vector product? But we will be using a bit of that. So I want to evaluate the surface integral of my function is just going to be z cubed ds, where s is r of, and remember here, right, for the sphere, our u's went from 0 to 2 pi, our v's went from 0 to pi, and that parameterization r, draw it up on me. Oh, sorry, not r of t, r of u v. That parameterization r of u v was 2 cosine u sine v I plus 2 sine u sine v j plus 2 cosine v k. All right. So if we want to use this definition, we want to evaluate this. So what is this? Well, by definition, right, this is the double integral. The surface integral is equal to the double integral over t of this function, but it's this function evaluated on the surface. Okay, so on this surface, right, the z component is 2 cosine of v. So we get 2 cosine of v cubed, right, or 8 cosine cubed v. And then I'm going to get times the norm of that fundamental vector product, dr du cross dr dv. Okay, and this is going to be dA or du dv. Okay. We previously calculated this, right? And so in the previous video, we calculated that to be, so we've got 8 cosine cubed v, and we calculated this to be 4 sine of v. And then we get du dv. And so what is this going to come out to be? So it's a double integral over t, but now remember t is just this rectangle. Right now we're integrating over the parameter space. So my u values are going to go from 0 to 2 pi. My v values are going to go from 0 to pi. And then what do I have? 8 times 4 is 32 cosine cubed v sine of v du dv. So now I have this iterated integral here. Well, the inside integral, right? The integrand doesn't depend at all on u, right? So this is a constant with respect to u. So all that happens when you integrate this with respect to u is it gets multiplied by the length of the interval, which is 2 pi. So you actually end up, I'm going to actually pull out. So you double this 32, gives you 64 pi. And then you have an integral from 0 to pi of cosine cubed v sine of v dv. Now, to evaluate this integral, you can actually, one way you can do a u substitution. The other sort of way, excuse me, the other sort of way to do this is just to recognize that this has come out of some sort of chain rule. Okay, and so the easiest way to do this is probably just sort of to guess and check what the antiderivative here is. And so I think we ought to get like a minus, oh, so sorry, we're going to still have the 64 pi. Okay, but then the antiderivative here will be something like, let's see, I think it's a minus cosine to the 4th of v over 4. Now let's see, if I took a derivative of that, what would happen? The 4 would come down, and you'd get 4 cosine cubed of v over 4. So the 4s would cancel. You'd have a minus cosine cubed of v times the derivative of cosine of v, which is a minus sine of v. The minuses would cancel. So I think that's right. And this will be evaluated at v equals pi and at 0 and take a difference. So let's see. So I get 64 pi times, if I evaluate this at pi, cosine of pi is -1. So that'll give me 1/4. Oh, wait, hold on. Sorry. Let me be careful here. Yes, sorry. That'll give me, it'll actually give me, be careful here. At pi, cosine of pi is -1, but it's raised to the 4th power. So I get 1. So I get minus 1/4. Okay. But evaluated at 0, cosine is 1. Right? So cosine of 0 is 1. This will give me a minus 1/4. So this becomes 0. And I actually get that the entire value of this integral is 0. Okay. Now, if you sort of think about it, this is maybe not so surprising that you get 0 here. This function you're integrating, z, is an odd function. So when you're above the xy plane, it's going to give you positive values. And those values are going to be constant on every sort of slice you take perpendicular of the surface, parallel to the xy plane. Below, you're going to get negative z values. And so basically things are going to offset as you integrate the top half of the sphere. You're going to get some positive value. But when you integrate the bottom half of the sphere, you're going to get a negative value. And those positive and negatives are going to be exactly equal to each other. And so they'll cancel out. Okay. But again, this just gives you some idea of stepping through the process, right? I want to integrate this function. So I want to take the surface integral of this function. So I evaluate this function on the surface, but I have to multiply by this, norm of the fundamental vector component of the parameterization. So then I do that, and now this just becomes a double integral over the parameter region t, right? And so that's how I actually calculate these things. So the actual calculation just becomes a double integral problem. You just apply the definition and we define the surface integral of a function in terms of a double integral over the parameter space. All right. Now, that's all well and good for a scalar function, but what if I wanted to integrate some sort of like a vector field? What if I want to integrate a vector field over a surface? Well, there we have to think about, well, what do we really want that to mean? Well, if I think about a vector field defined on a surface, one of the most natural sort of examples of that to think about would be, imagine my surface, is some sort of net, right? And the vectors at each point on the net are representing some sort of fluid flow. So the fluid is flowing across this net, and this net forms some surface, right? And you might want to try to understand, like, well, how much fluid is actually flowing through that net? Or, if you know other things like there's some density of something in the water that the net's going to catch, and the fluid flow, you might want to know how much stuff you're going to catch in the net, right? So when we go to think about that, we want to define some sort of surface integral over a vector field, then we're going to actually define it in the following way. So again, I have some smooth parametric surface, and I want to imagine that it has a unit normal vector. So remember that the fundamental vector product here is normal to the surface, but I'm going to normalize it so that I get a unit vector. Okay, so n here is simply a unit normal vector. So for a vector field f defined on the surface S, the surface integral of f with respect to that normal vector, well, we're just going to take the surface integral of f dotted with n. Now, why are we going to take that? Why are we taking that dot product? Well, if again, I imagine I have some surface, but now at each point on this surface, right, I have different vectors defined. Okay, and these vectors, this is my vector field, so these vectors don't need to be normal to the surface. In fact, they're probably not, right? And they could point all sorts of different ways, right? But if I think of wanting to capture with this surface integral sort of the flow across the surface, then, for example, what I really want to do here is I probably want to come here and let me figure out what component of this is actually normal to the surface. So what I do is I take some normal vector. So let's say this is my normal vector to my surface here. This is my vector field defined at that point. Well, if this is a unit normal vector, then the component of f, the component of the vector field in the direction of the normal vector, okay, and actually let me write that as n hat, right, because that is a normal vector, or sorry, a unit normal vector. So the component of f in the direction of that unit normal vector, since it is a unit normal, is just f dot n, okay? So what we're really doing is we're adding up sort of for all of these vectors defined on the surface, how much of them is in the direction of the normal vector, right? And so in some ways what that does is that gives us flow across the surface, right? So you also sometimes hear these referred to as like flux integrals, right? And that, especially in physics, they might describe these as flux integrals. Now, once you sort of define that in that way, so now this is actually perfectly well defined because f dot n is a scalar, right? So now I have a scalar function here that I'm taking the surface integral of. Now, if I look, though, this doesn't look like what I had before. So let's think about if I were to apply my definition of the surface integral here, I would say, okay, this is a double integral over t of my scalar function evaluated on my surface. Okay. Times the norm of the fundamental vector product. Now again, notice that doesn't quite look like this yet. Okay. But what we remember is that this normal vector, this unit normal vector, is defined in this way. So if I plug that in, right, for n, then plugging this in for n, what's going to happen is I'm going to get cancellation of the norm of the fundamental vector product, which is in the denominator here, right? And then this will simply become this expression above. Okay. So really, to define the surface integral of a vector field, it's just saying, oh, when we say we're going to take the surface integral of a vector field, we're really taking the surface integral of the scalar function, which is the vector field dotted with the normal vector, the unit normal vector. But in the process of doing that, right, we really get this sort of simplified form here. Okay. Now, one thing that's sort of not totally clear here, though, is when I take a surface like this, and I say take the normal vector to the surface, if I, for example, was at this point, when I say normal vector, do I mean this vector or this vector, right? There are, in this case, two choices for the normal vector, okay? So I actually do have to sort of make a choice here. Often this depends on sort of which way I care about measuring things, right? So it's just a choice of orientation. Now, this does get into a deeper question of for which surfaces is this really a choice I can make, right? Some surfaces, like for example, a Mobius strip. So if you've seen a Mobius strip, the idea is, imagine you took this little rectangular strip, but then you put a twist in it and glued the two ends together. Okay. So in that case, what happens is you end up with, and I don't know if I can, used to be able to draw something like this, but I'm not sure if I can anymore. Let's see. Connect everything appropriately. All right. So the idea is this is like a two-sided, well, you sort of imagine this had two sides, right? But now over here, if I choose, say, a normal vector here, and then I allow it to move around, like if I just keep moving this, if I sort of imagine, I want to say this is up. Now I try to follow this along, but what happens is that as I follow it along and bring it all the way around, when I get back here, it's actually pointing in the opposite direction. So this Mobius strip doesn't really have two sides. There is no sort of well-defined normal vector. So we would actually say this surface is not orientable. Okay. Now, I don't want to spend a lot of time in this course talking about, orientable versus non-orientable surfaces, but I do want to emphasize that for surface integrals, right, you do have to make a choice of which direction, assuming your surface is orientable, you need to sort of make a choice of which normal vector, you're going to deal with. Oftentimes, it will be obvious from a particular context which normal vector you want. But you need to make sure that the one you're actually calculating with is the one you want, right? Do you want the one that points in, say, the positive z direction, right? So you might say, oh, okay, I need this one, right? If you notice on this surface, probably one choice of normal gives you that all of the normal vectors have a positive z component, right? So that would be one way to sort of specify your particular orientation of the surface. This is really no different than, for example, choosing an orientation of your curve when we did line integrals. It's simply that in this higher dimensional setting, you can have weird things happen, like, for example, having non-orientable surfaces. All right. So again, just to remind ourselves some of this, let's actually look at one more example. This time looking at the surface integral of a vector field. And again, we're going to keep our same surface here being that sphere that we've been using. Okay. So now let's for this example, let's let f be xi plus yj plus zk, and s be that same sphere of radius 2. Okay. And now I need to give you an orientation, right? oriented by outward pointing normal vectors. Okay, so again, I have the sphere, and I want my normal vectors to be the ones that are pointing to the outside of the sphere, to the unbounded part of R, not into the sphere, right? Now, my goal then is to evaluate the surface integral of F. All right. Now we're going to sort of do this two ways. The first is to just sort of use the definition, plug it out, see how it goes. Now the second is a little more nuanced, a slicker way of doing it for this particular example. So in the first way, right, we first need to calculate this vector n hat. Okay. Now, notice that we've already found in the previous video that fundamental vector product, which gave us a vector which was normal to the surface. So we had that dr du cross dr dv was minus 4 sine v times the vector cosine u sine v I plus sine u sine v j plus cosine v k. Okay. But now I need to divide through by its norm. Remember that we already calculated its norm also, though. Right. And that was just 4 sine of v. And so what we get is that the unit normal we can write as minus cosine u sine v I plus sine u sine v j plus cosine of v. Okay. All right. Now, let's be a little careful, though, because I need to ask myself, well, in what direction is this vector pointing? Well, one nice way to figuring this out is like pick a particular, like what happens when v is, for example, 0, right? When v is 0, this is 0, this is 0, we're at the top of the sphere. Okay. So when v is 0, we're sitting here at the top of the sphere. This is giving us that our normal vector would be minus cosine of 0 would be minus 1k. This is giving us the inward pointing normal, right? But I want the outward pointing normal. So what do? I just take the opposite sign. Okay. So because I want this oriented with outward pointing normals, I'll just take the opposite sign. That will give me my outward pointing normals, right? Okay. So it's handy here again. You can just check one particular point to figure out whether you're pointing in or pointing out, and that'll help you realize that you should flip your sign. All right. So now that I've calculated this, right, I want to go back and I want to evaluate the actual integral itself. Now, I want you to notice something. We can sort of do this two ways. So I have the double integral, or sorry, I have the surface integral of f dot n ds. Now, one way I could do this is I could go back to, this is a scalar function, so I could compute f evaluated on the surface dotted with the unit normal vector evaluated on the surface, multiply by the norm of that fundamental vector component or fundamental vector product, and I could calculate it that way. But what we saw earlier, or what we saw just on the previous slide, was that a slicker way to do this is just take f and evaluate it on the surface, and then just dot product it, not with the unit normal, but just with the fundamental vector product here. You don't actually need to normalize it, right? So in this case, what we can do is take f, right? So it's the vector x, y, z, but for x, I'm going to plug in the x component of my parameterization. So this is going to be 2 cosine of u, sine of v, I, plus 2 sine of u, sine of v, j, plus 2 cosine of v, k. So again, notice what I'm doing here is I'm taking my function, which is x, y, xi, yj, zk, and I'm plugging in for everywhere I see x, which is only here, I'm plugging in the x component of my parameterization. Plugging in the y component of my parameterization here, z component of my parameterization here. And I'm going to take a dot product of this now just with this fundamental vector product. But now this is where I have to be careful. Remember that when I was finding the unit normal here, I had to negate. I need to negate here also, right? Because this is normal to the surface, but pointing in, I need that to be pointing out, okay? So in this case, I want 4 sine v times cosine u sine vi plus sine u sine vj plus cosine vk. A lot of bookkeeping here. All right. Now, if I go through and I calculate out, so I need to write out this dot product. So I've got a 4 sine v, that would come out front. And then I'm going to take the product of the I terms plus the product of the j terms plus the product of the k terms. If I do all of that, I want to save us a little bit of time here. If you write all of that out, you should get that this is, so you'll get a constant of 8 that comes out front. And then you'll get a double integral of sine of v du dv. And of course, we're integrating over t now, so this goes from 0 to 2 pi, and this goes from 0 to pi. Okay, so all of this, once you collapse it down, should collapse down to sine of v. Check that out. You should be able to work that out. Now, once you do that, now this is just a double integral over a rectangle, actually, right? So if I integrate sine sine of v, but integrate with respect to u, this is a constant. So I'm just going to get a 2 pi, right, that comes out. So I'll pick up a 16 pi, and then I'll have an integral from 0 to pi of sine of v dv. And now that simply becomes a 16 pi times the antiderivative of that is a minus cosine of phi evaluated at pi and 0, and take a difference. So at pi, this gives me -1. So negative 1 is 1 minus, I get 16 pi times, so it gives me negative, it gives me a 1. Then a minus at 0, I get -1. And another 2, so I get a 32 pi. And so 32 pi is my final answer here. All right. Now, as I mentioned, this is sort of just plugging and chugging through the definition. What if I wanted to take a slightly more nuanced approach? Okay, how else might I be able to think about this particular problem? Well, it turns out that I can actually benefit slightly in this case from sort of ignoring the parameterization piece of it. So one other sort of way I can think about this is I can think about the particular surface S. So S is a level set of the three variable function x squared plus y squared plus z squared, right? So a level set is just, right, if I take this and set it equal to a particular value, x squared plus y squared plus z squared is equal to 4, then that gives me the sphere of radius 2. So my surface S is just a level set of this. And so one way, when you have a level set, one way to get a normal to a level set is just to take the gradient. So the gradient of f of x, y, z, right, would just be the vector 2x, 2y, 2z, which you could then normalize, right? And to get the unit normal here, you would divide by the norm of this. So the norm of the gradient of f would be, you just write the whole thing out, it just becomes 2 times square root of x squared plus y squared plus z squared. Okay. And so your normal vector becomes 2x over 2 square root of x squared plus y squared plus z squared, comma, 2y over 2 times the square root, 2z over 2 times the square root. And the 2's will cancel. And if you think about this as just being, right, on the set that I'm interested in, the square root of x squared plus y squared plus z squared is just 2. Right, because I'm really interested in the level set where f of x, y, z is equal to 4. So x squared plus y squared plus z squared is equal to 4. So the square root of x squared plus y squared plus z squared would be 2. That's just the radius of that sphere. So the particular normal vector to the surface I'm interested in is this. Okay. And notice that this actually does point out, right? This is a unit normal vector pointing out. All right. So then if I go to calculate the double integral, or sorry, the surface integral of f dot n ds, then I could just write down actually, what are these things? So f is just x, y, z. N is this vector, okay? And so what I would end up with is just that I want the surface integral of, this would end up being x squared plus y squared plus z squared all over 2. Yeah. But now again, remember that this, right, this is just going to be 4 because I'm looking at the level set x squared plus y squared plus z squared is equal to 4. So you get the surface integral of 4 over 2 ds. So you actually get that this is 2 times the double integral, or sorry, the surface integral of s ds. But remember, we said this is just the surface area of the sphere of radius 2. The surface area of that sphere, so I'm going to get 2 times the surface area of the sphere of radius 2 is just going to be 4 pi times 2 squared. So it's just going to be 16 pi. And so I end up with 32 pi. So in this case, it actually turns out that you can do some trickery because you can view this particular surface as a level set of some higher dimensional function, and you end up with things that algebraically simplify nicely. This is not a trick that is standard. The first way I showed you is sort of the standard way of doing these, but sometimes you do benefit actually from not dealing much with the parameterization. Now, the other reason I like showing you this is what you notice here is that this didn't depend on the parameterization, right? As we have seemingly defined things, everything, right, is in terms of having something to do with this fundamental vector product, which has something to do with a parameterization. You could worry that a surface integral depends on the parameterization that you choose for your surface. Now, as I've said before, that would be pretty bad actually, because that would mean that this integral isn't about the surface itself, but rather about the parameterization of the surface. But as we've seen, at least in this example, it's seemingly the second way of calculating it had nothing to do with a particular parameterization. Okay. So the last thing we'd like to show in this video about surface integrals is that they're actually independent of the particular parameterization you choose for a surface. Okay. Now, we won't show every detail of these proofs, but we'll sketch out the main ideas just to help us see that we need not be worried about this, that indeed, as long as your parameterizations actually parameterize the same surface, you should expect that the value of your surface integral will be unchanged. All right. So the first sort of thing is sort of a stepping stone to get us there. Imagine you have sort of two smoothly equivalent functions. So I'm going to imagine I have a little r and a big R. And really what I want to think of is that big R can be written as little r composed with some other function g, where this g is just some one-to-one continuously differentiable mapping of a region B in the ST plane onto a region A in the UV plane. And then our claim is if we do that, so if little r and big R, again, they're sort of mappings from one region to another, such that they are equivalent to each other under that mapping G, then the fundamental vector product of R with respect to S and T ought to be equal to the fundamental vector product of little r with respect to U and V times this quantity duv dst, which you'll remember, this is just a scalar function here, right? Okay. So really what this tells us is that if little r and big R are related in this way, they're smoothly equivalent functions, then their fundamental vector products are just scalar multiples of one another, right? Where this scalar is just, determined by some Jacobian of this 2x2 matrix. Okay. This is the piece that I'm just going to sort of sketch out, in part because most of the calculation is just, or most of the proof is just doing some calculation. So the main idea, right, is that, so you have that capital R, so you have capital R of ST is equal to little r composed with capital G of ST. Okay. Now, again, in general, R is taking as inputs U and V. So this G of ST is really spitting out, right? It's a vector valued thing, which is giving you out U of ST I plus V of ST J. All right. So the whole idea is that you want to calculate the partial of R with respect to S. Okay. So you need to apply a chain rule, right? And so if you just apply the multivariable chain rule, so you get this as dr du times times partial u partial s plus partial r partial v partial v partial s. Okay, and similarly, dr dt is partial little r partial u partial t plus partial r partial v partial t. Okay, so this is just applying the multivariable chain rule. And then you take cross products. Okay, so you take the cross product of this with the cross product of this. So I'm going to sort of abuse notation a little bit. These are equations, but just imagine I was just taking the cross product of these things. When I do that, I'm going to end up with, so I'm going to use some properties of cross products, namely that we're going to end up with. Let me just make sure I get this right here. dr du cross dr dv times, and we'll get partial u, partial s, partial v, partial t, minus partial u, partial t, partial v, partial s. And if I look at this, this is dr, okay, this is the fundamental vector product of r with respect to u and v, of little r with respect to u and v, times, now this is just the determinant of the matrix du ds, dv, t, du, dt, dv. Okay, which is precisely that thing we called earlier duv dst. And from here to here, let me just point out, like you're going to take, so you're going to get a dr du cross dr dv, and there you'll pick up a du ds dv dt. Okay. Then you're going to get a dr du cross dr du, but the cross product of a vector with itself is just 0, so that goes away. You're going to get dr dv cross product with itself. That's going to go away. And then the other term we end up with is a dr dv dr du. You get a dv ds du dt, which is here, but then you swap the order of those terms in the cross product to get another dr du dv dt, and that negates that. So that's where all of that falls out. So again, this is really just a computation, right? But again, the important thing is that it shows us that the fundamental vector product of the parameterization with capital R, it's just some multiple of the fundamental. They're always pointing in the same direction, right? That's really sort of the key. They're pointing in the same direction, even though they may have different magnitudes at particular points, right? So when I say they're multiples of one another, they're not constant multiples of one another. That multiple could change at each point, right? That really very much depends on the particular parameterizations, but they are always pointing in the same direction. That's sort of the key, that two parameterizations of the same surface can't give you different normal vectors, or well, they can't give you different normal vectors pointing in different directions. All right, so once we know that, it turns out that we can say more, right? So if we let little r and big R be, again, smoothly equivalent functions, as described in that previous theorem, then if the surface integral with respect to one parameterization exists, then the surface integral with respect to the other parameterization also exists, and the surface integrals must be equal to one another. Okay, so again, this basically says we need not worry about what parameterization we choose if they are smoothly equivalent functions, right? So they're sort of parameterizing the same surface, then it doesn't matter which one I pick. If one of them exists, the other will exist, and they'll always give me the same value. So I don't have to worry about which parameterization I choose, which is really nice. It'd be really unfortunate if I did have to worry about that. Okay. Fundamentally, I'm not going to work out either for this the full proof, but sort of the essence of this is, you start with one. So imagine that you have, with respect to the parameterization little r, f ds, right? And so by definition, that would be equal to the double integral over the region A of f of r of uv times the norm of the fundamental vector product dr du cross dr dv. Okay. And now really what you want to do then is just use this integral and transform it into a region, an integral over the region B in the ST plane, and that function G that sort of explains to you how these are equivalent is going to be the way to go about doing that. So I can re-express this as a double integral over B of f of r of g of st, and then I'll get a norm of dr du cross dr dv times this determinant now this comes from sort of the change of variables formula for double integrals, right? So if I'm going to do a change of variables, right, that's fine. I plug in my change of variables here. That's going to transform my region, right? So now G maps B to A, okay? Same thing here, but now the only difference is that I pick up this Jacobian matrix that sort of comes from my change of variables, and that's precisely this quantity here. But now if I look at this, right, this is just equal to, this is capital R of ST, and this, by our previous theorem, is precisely dr ds cross dr capital R dt in norm. Okay. And so this whole thing actually is just the integral over capital R of B of f ds. Okay. So it turns out that it doesn't matter what parameterization we choose. By properties, well, really by the definition of the surface integral and then properties of change of variables of double integrals, we'll actually be able to get back to see that the same, that if one of the integrals exists, the other must exist, and they must have the same value when they exist. All right, we will stop there. So what we will do moving forward, right? And I would encourage you to, take some time, pull up some old Calc 3 problems, maybe walk yourself through calculating a couple of these things. They're nice to just get back in the habit of, and I'm happy to, check your work on something or answer questions if you go back to review this and you've had some trouble. But what we really want to do now is move on into looking at some of the theorems, the big theorems from Calc 3. So in the next video, we will start by exploring Stokes' theorem and Green's theorem, which really tell us something about how we can relate the integral of some function over a region to an integral over the boundary of that region. Again, these are going to be fundamental theorem of calculus type theorems, just for higher dimensional types of derivatives and integrals. So that will begin in the next video.